Good morning, class. Today is October the 12th, and so this is the video for October the 13th. And it is on solar cells, or solar panels. We'll start with solar cells. And for some of you, this may be a little bit of a review, particularly electrical engineers, perhaps. For other, this will be new, and so we're going to, start from the beginning. And all of you have probably seen solar panels. So, a solar panel is this relatively large rectangular thing, and then on the solar panel you've seen solar cells probably. So we're going to describe today how the solar cells work, and if I can, I know we're going to expand this a little bit, but if I take this solar cell and I make it a little bit bigger here, all right, what you will see today is this solar cell consists of two layers of material that are called N-type and P-type. But for now, what I want you to realize is that the most important thing about a solar cell is that with a positive voltage across it, it can supply current. So there are several things that I want you to understand about the solar cell in terms of its voltages and currents first. All right, and what we're going to show is that particularly there's something called the current voltage relationship for the solar cell. And the first principle is that a solar cell has plus and minus. That is to say, if you can't pick up a solar cell because it's a piece of semiconductor and say that, oh, it's a plus and minus. But for example, what we're going to show in the next lecture is how the solar cells are connected together. And certainly for the solar panel, it has a plus side and a minus side. And the same thing's true for the solar cell. It has a plus and a minus, meaning one of these terminals, one of these sides is the plus side and the other side is the minus side. And the way I have it drawn, that's like this. So, and so the number one lesson, or the first lesson I want you to have from today's lecture is that if someone ever comes to you and says, "Oh, I have a new way of generating solar electricity, a new device for producing electricity in the sun," your first question is, what is the plus terminal? And if they can't answer that, well, then it's not true. Because a solar panel, or any device for producing electricity in the sun, has to have a plus and a minus terminal. All right, now, we're going to learn two things today. The first thing is that a solar panel is a diode. And a diode is a device which, if you, now you have to remember here, if I have a negative V, that means putting a positive on this terminal. All right. If I put a positive voltage on this terminal, meaning a negative V the way I've referenced it, I get no current. But if I put a positive voltage on the other terminal, I get current. So this is sometimes called a unipolar device. It's not important how you think about it. But basically, this device as I have drawn, okay, and the way I've referenced the voltage, meaning that if I apply a positive voltage to that terminal, that's a positive V. If I apply a positive voltage, I get current. But if I apply a negative voltage, meaning a positive voltage to this terminal, I get no current. And so that's unipolar or rectifying, however you want to talk about it. But so it's sort of built in to how it behaves. What's the plus terminal? Now this is in the dark. And then what you will see is that in the light, it looks like this. So if I take a solar panel and I measure the current voltage relationship in the dark, all right, I get this characteristic. And if I measure it in the light, I get this characteristic, where it's just simply been shifted down by an amount called I sub L. And the second principle, the solar cell provides current away from it with positive voltage. Okay, now what do I mean there? What I mean is that, and let's draw it over here big so we understand what I'm saying. All right, here's my solar cell, P and N. Now I'm going to shine a light on it. Okay, that means that with a positive voltage across it, I get a current in this direction. Now, for normal devices, okay, and so it has a characteristic that looks like this. Now, a normal, let's say, let me do a resistor, because we'll be doing resistors later. Okay, if I apply a positive voltage across a resistor, I get current into the resistor. And so it has a current voltage relationship that looks like this. And so a solar cell, particularly in the light, is characterized such that for a positive voltage across it, it supplies a negative current, meaning a current going out of the device. As opposed to like a resistor, you put a positive voltage like across it, you get a current into the device, meaning a positive current for a positive voltage. And what that means is that I can, for example, hook up a battery across it. I'll draw a battery. So I can hook up a battery across it, meaning that has a plus and minus like that, say a 12-volt battery or your cell phone battery, and I can charge it up. Okay, so again, if someone ever comes to you and says, I've invented a new way of producing electricity in the sun, there are two things. First of all, okay, your first question is, what's the plus terminal? And the second question is, can it supply current away from the device, meaning a negative current reference to the device, if you put a positive voltage across it, which a solar cell can. Okay, so I'm going to erase this part over here, and we're going to start describing how this device does that. Now, I've written these things P and N, and what do I mean by that? Well, we have to do a little bit of semiconductor physics. Okay, that sounds serious, but it's not too bad. Okay, and You know enough to do this because you've done some chemistry in the course or previous to the course. And so you know the octet rule. And so you know that if I take silicon, okay, pure silicon, okay, silicon is group 4. Now, what group 4 means is that it has 4 valence electrons. And so if I draw the valence electrons for every silicon atom, it looks like that. And so silicon forms a covalent crystal or solid, meaning this is what silicon looks like. It forms bond to its 4 nearest neighbors. And since it has 4 valence electrons and each neighbor supplies a valence electron, there are 8 around each one. And so it's a very stable solid. Now, because all the valence electrons are locked up in bonds, it is insulating. It is an electrical insulator. Now let's say I take this silicon solid and I replace one of the silicons with an arsenic atom. Now arsenic is group 5. So the arsenic atom has 1, 2, 3, 4, 5. It has an extra electron. And that extra electron can move around the solid and conduct. Now, we're going to show in a minute p-type, but just jumping ahead, this is n-type because the charge carrier is negative. It's an electron. You may be wondering, how can the charge carrier be positive? Well, I'm going to show you that now. This is called doping, and that refers to replacing some of the silicon atoms with what's called the dopant atom, in this case arsenic. All right, so that's n-type. All right, let's go up here, and now let's replace that silicon atom with a boron atom. Now boron is group 3, meaning it has 1, 2, 3 valence electrons. And so there's 1 missing. Okay, and we call that a hole. Now, there's 2 ways to look at what this missing electron, how it behaves. One way is with a pool table. So I'll draw a pool table here. Everyone knows a pool table. Oh boy, I don't know if I'm going to be able to draw this. I'll draw some of them here. Okay, let's say you took a pool table and you filled it with cue balls, but you took out one. right? Okay, so that's what I've done here. I've taken out one of the valence electrons. Now, think about it. If I had a pool table filled with pool balls, all right, if it was full, none of them can move. And so that's like pure silicon, that's an insulator. But if I take out one, well then that one can move there, and then that one can move there, and et cetera, et cetera. And the same thing over here, this valence electron can move there, and so that makes a hole there, and so on and so forth. And so if you did this on a pool table and you used time-lapse photography, it would look like there was a hole moving around. And in fact, that hole behaves exactly like a positive charge. Now, another analogy is a bubble in water. Now, you have to imagine you're up in space, and so there's no gravity, and you have some breathing apparatus on. So you're sitting there in this tank of water, and somehow you've made a little bubble, meaning a hole basically, some missing water. And if you took your finger and you pressed on that bubble, it would feel like it was resisting you, like it was a particle, like it had mass. Okay, obviously it doesn't have mass, there's nothing in it. But it behaves like a massive particle, meaning it resists your finger pushing it. Because when you're pushing it, what you're really doing is you're pushing all the water around it. And so you can, it's like you can tap it and then you can watch it move or something like that. And so it behaves like a particle, even though it's nothing, okay? It behaves like a particle because there's something all around it. And the same thing is here. The something all around it are all the other valence electrons, and it behaves like a positive charged particle. All right, and we call this, and so that hole can conduct electricity, and we call this p-type because the charge carrier is positive. Okay? P-type, N-type. Now, okay, you look at the board here, you see I've kind of done something interesting because I've put P-type on the top and N-type on the bottom. Just like over here, I had p-type on the top and n-type on the bottom. All right, okay, and that's exactly what we're going to do. We're going to make what's called a p-n junction. Now, I'm not going to tell you how you make that. That's another course. But if I made that, and I'm going to erase this, and I'm just going to draw it on its side. So I'm going to make my p-n junction, and I'm going to turn it on its side just so we can kind of tell what's going to happen a little bit easier. And I'm going to draw it a little bit elongated. And there's my junction, and this is p-type, and this is n-type. So I took that and I turned it on its side. And here's one terminal, and here's another terminal. But before we get to applying voltages, what happens when I put this, imagine, okay, this isn't how you make it, but imagine I took the p-type and n-type and I just sort of slapped it together. All right, there's holes over here, and there's electrons over here. All right, now what happens is that when you put them together, it's kind of like if you had red liquid in one chamber and blue liquid in another chamber, and all of a sudden you lifted the valve or the divider between them, the holes are going to go over there and the electrons are going to go over there. Now, to think about what happens next, all right, you have to remember that when a hole goes over there, all right, it leaves behind a negative charge. All right, let's look at p-type. P-type is our arsenic, our boron. Silicon, 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 and there's our boron. All right, when it had its 3 electrons, all right, it was neutral. But when the hole left it, okay, it became negatively charged because a positive hole left. And so when these holes leave, you start getting what's called a space charge layer on this side of negative, I'll call them ions, meaning the negatively charged boron, if that was your dopant over there. And so we're going to designate that with a minus sign. Now, same thing for electrons. When these electrons leave the left, okay, and that's kind of easier to see maybe, the N-type, silicon, 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 here's our phosphorus, silicon, 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 and here's our phosphorus with its 5 electrons, and this one leaves a negative electron. It leaves behind a positively charged phosphorus atom. And so you develop a positive fixed charge over here of positive ions, those arsenic atoms. Now think about what this means, okay? Remember electric fields. Let me write out electric fields so we don't distinguish it from energy. Okay, electric fields go from plus to minus, and so this results in a built-in electric field. And that electric field then acts to stop the holes from moving and stop the electrons from moving. I mean, another way you can think about it is that, so these negative ions over there, where they repel those electrons, so they can't get over anymore. And those positive ions over here repel the holes, and so they can't get over anymore. And we go into equilibrium. Now, so in equilibrium, I have a negative layer of charge here and a positive layer of charge here, and there's no net movement of charge in any direction. All right. Now, what happens then? Now, okay, I've reached equilibrium, so this has stopped. Okay. I have my space charge layer, minus, plus, and it extends to a certain layer here. And what's happening now? Well, I said there's no net movement of charge, okay? There's still all these holes over there, and they can move in that direction a little bit. And we're going to describe this as being an energy barrier. So you still get a current of holes from P to N, and that is proportional to, all right, now we haven't covered Boltzmann physics, we sort of touched upon it and things like that. I'm just going to write this out, e to the minus E barrier over KT. Now, what does this mean? Okay, it means that there's an energy barrier here. This has units of energy. KT is the thermal energy. Where where T is in Kelvin and K is Boltzmann's constant. So what I'm telling you is that we're in equilibrium, but you still have holes moving in that direction because there's all these holes over there. And the barrier, it can't, I mean, what this is basically saying here is that when you have thermal energy of holes, some of them are going to have enough to go over that barrier. All right, so, well, but I said there's no net movement of holes, so what's going on? Well, okay, what I haven't taught you is that there are holes on this side. Okay, there's a very small number of holes. And they are moving from N to P. Now, what is that proportional to? Well, okay, where they come from is from thermal. I'll write it up. Ripping electrons off bonds. Remember the picture I showed? Okay, silicon. Let's just imagine there's a bunch of silicons here. Okay. And I said there's these valence electrons. And I said they're locked up in bonds, so they can't do anything. But they can, because at room temperature there's enough thermal energy that they can rip off of a bond. And so when they do that, they leave a hole behind. Now, I said things are in equilibrium, and what that means is that in equilibrium, that energy it takes to rip that electron off the bond has to exactly equal the barrier. And so these are equal. And you have holes moving this way, and their statistics are dictated by that barrier. There are holes moving that way. Now remember, if there's holes here, they like going in that direction because they see these negative ions, they want to go there. And they have the same quote-unquote barrier. The barrier is really the barrier of ripping off of a valence bond, but things have worked out so that they exactly equal each other. All right. Now the same thing with electrons, and I'm not going to write that out because there's no necessary. This is at zero bias. No voltage. Now let's say I put a positive voltage on here, and this one goes to ground. It's helpful to remember for diodes, positive means applying a positive voltage to the P side, P positive. All right, and now what happens? Okay, so this is with no voltage. Now, with positive voltage, then the built-in field is, and this is where I miss being in person, okay, and so you know, those of you watching, all right, I put a positive voltage on the P side, all right. Now, I said that these ions here create an energy barrier, and so when I put a positive voltage in the V side, what happens to that energy barrier? What effectively happens to it? Does it get smaller or does it get bigger? All right, I'll think about it. All right, class, who knows the answer? When I put a positive voltage barrier, does it get bigger or smaller? Bigger or smaller? All right, the answer is smaller because remember what's happened. This energy barrier. I mean, think of think of these electrons, or well, either way, think of the holes. The energy barrier there's positive, negative, that stops these holes. But if I put a plus voltage there, it's like it's pushing them from behind, kind of. And so it effectively lowers the barrier. Now then, by the way, just backing up, I didn't write it out. The same thing is happening for electrons, this sort of balance thing here. Okay, then holes from P to N is proportional to a lower barrier. Now, how much is it lowered? Well, remember, energy is equal to charge times voltage. So I put a voltage there, so it's where this is the charge of an electron. And I know there's little e's floating all over the place because you have the exponent here, but that e there is the charge of an electron. Now, what about the other way? The holes from N to P, what is that proportional to? Okay, and here again, you know, in class I would go, okay, here the holes going the holes over here going that way. Has that changed at all by applying a positive voltage? And you know the question is, okay, is it no? And the answer is no. It hasn't changed at all, because that quote unquote barrier to them happening was occurring at the bond level. All right. Those bonds don't care what's happening with the voltage way over here or something like that. They only know it takes a certain amount of energy to rip that electron off of that bond. And so that test stayed the same. And so, going over here, I can write out the net current. Now remember, okay, the same thing is happening with electrons as happened with holes. It's just repeating the same equations over again. And because we're using proportional signs, we don't need to do anything. The total current then is equal to the holes from P to N minus the holes from N to P. Okay, because then it's because you subtract that. I mean, holes going one way minus holes going the other way is your net current, and that is then equal to or proportional to what I've written there: e to the minus e barrier minus EV over KT minus e to the minus EB over KT. Because this one, okay, now think about it, all right? Since the barrier, this is e to the minus a barrier that has gotten smaller, so that has gone up, all right? And so this is bigger than that, because this is e to the minus a smaller number. And so I can write then, putting in a proportionality, which let me look and see what I used in the notes. I just used A. Okay. I can use a proportionality constant. I'll just use A. And let me bring out one of the even. Okay. Now, for your homework problem, I'm going to leave it written the way it is. Okay. And let me just leave it that way. Okay. So A. Well, okay. Let me bring it out. But we'll talk during the chat session tomorrow about your homework problem to make sure you understand it. But let's bring it out. E to the minus EB over KT. So I brought that out. Times, now here, plus plus, or minus minus plus e to the EV over kT minus 1. So that is the current voltage characteristic of a diode. In the dark, and that is exactly that curve. So we're going to stop with this today, okay, because it's kind of a lot to take in. We're going to talk about it tomorrow. We've derived the current voltage characteristic. We've gone through about half a semester of semiconductor physics, but you know, you get it. There's P in the N, there's barriers. There's barriers that change with voltage and barriers that don't. And we've derived the current voltage relationship. Now, it's very important that you understand something here for you to be able to get started with your homework problem. The current voltage relationship, all right, is such that, think about it, if temperature goes up, right, this term, e to the minus that over kT, goes up. All right. See, if you just looked at this term here, you might think that as temperature goes up, current goes down, because that's e to the minus something and the t is in the denominator here. That's not right when you take into account the fact that, okay, EB is always greater than EV. Now, why is that? Well, because, okay, I'm increasing V, increasing V, all right, and I start getting current. If I ever reach the point where I eliminate the barrier completely with my applied voltage, the device would blow up. Okay, your current would be, you know, way up there above the roof. All right, so this EB minus EV, that's always positive. So this term in the exponent is always negative. And so as temperature goes up, I have e to the smaller a negative term. And so when temperature goes up, current goes up. With temperature goes up, current goes up. And of course that makes perfect sense, because all of this, you know, the back and forth and everything else, all of this was via thermal energy, ultimately. And so the more thermal energy, the more current you're going to get. And what that means is that it effectively moves these curves this way. Oops. This is in the dark. I'll put T there. All right, so I'm not going to jump. I mean, I know your homework problem requires you to do this in the light, but we're going to stop there. We've derived in the dark what happens. What happens in the light is easy to understand next, and you kind of understand what's going to happen here, which is that this curve is going to do this with increasing temperature, because the whole thing is just shifted down in the light. Tomorrow, or in Wednesday's lecture, I'll explain why in the light it does that. But let's stop here. We've derived this equation, and the only thing I want you to understand from this equation, to make sure you understand, is that when you take everything into account, and you take into account that the barrier is always bigger than EV, current goes up with temperature. Okay, and we'll stop there for today.